and welcome to this tutorial about influence diagrams in Fantasia. Influence diagrams represent a very important step for our development of conversational AI in an interpretable way. So let's start from, in general, Bayesian networks. We have already discussed this in a dedicated video. In general, Bayesian networks are probabilistic graphical models. Graphical is an important word. They are organized in a graph, so they can be related to, for example, Neo4j structures. They allow specifically to describe the influence that some variables have on other variables, so that in general we can take decisions upon these. Take note that Bayesian networks do not explicitly model decision making. Of course, we can reason upon the probability distributions that we get on Bayesian networks with dedicated scripts, for example. But there are models, and influence diagrams are these models, that explicitly take into account decision making and combine it with probabilistic graphical networks in general. So this is the classic example of a influence diagram. This example you can find in mostly every textbook that describes influence diagrams. There is an Agrum tutorial about influence diagrams. Agrum is the library upon which influence diagrams and Bayesian networks are implemented in Fantasia. So we will be using Agrum even for our examples. In general, this problem represents the need to take a decision when you're going to take a vacation. So in general, when you want to take a vacation, when you have some holidays, you have different options at your disposal. You have, for example, outdoor activities and indoor activities. Your level of satisfaction is influenced by the combination of the weather condition that you will actually find on the day of your holiday and the decision that you have taken about the activity to perform. However, when you take your decision, you don't have available the information about the actual weather condition. You only have a prediction, an estimate about what the weather will be in the future when you will actually perform your vacation activity. So at decision time, you only have the weather forecast, but your satisfaction depends on the actual weather and not on the forecast. An influence diagram helps you take a decision by combining priors, representing what the weather is usually like, and the accuracy of the predictor, in this case the weather forecast. And it allows you to take the decision that most likely maximizes your level of satisfaction. So here's the tables that we want to include in our decision model. First of all, we have information about the weather, the variable W. And let's assume that in the place that we're going to have our vacation, it is sunny 60% of the times and it's rainy 40% of the times. Next, we have the accuracy of our predictor, our weather forecast. And we know that when the weather has been actually rainy, the weather forecast predicted the rainy class 75% of the times. In the other cases, the predictor said that it would have been sunny and the rain came. On the other hand, when the weather is actually sunny, the forecast here predicted rain 15% of the times and sunny, so it was right, 85% of the times. In this case, we are modeling the information that it is slightly easier to predict when the weather will be sunny rather than when the weather is rainy. This is the kind of information that you get, for example, when testing your machine learning algorithm on a test set. So if you did your training procedure correctly, you have an estimate of the performance of your machine learning algorithm, and you can include this information in the decision model. In this sense, it is very important for you not to discard the fact that predictors typically give you probability distributions. If you just take the highest probable class, in this case, and only consider that, you're actually not considering the information that your machine learning algorithm may be giving you about the fact that its prediction is uncertain. In many cases, it will be the machine learning algorithm to communicate to you that the decision is not that easy to perform. In here, with influence diagrams, we are informing the decision model of both the probability of the weather to be rainy or sunny and the kind of mistakes that the predictor does, even with different situations. Next, we have a utility table. So we combine all the possible values of weather and activity to inform the model of what happens from a rewarding perspective. So if the weather is rainy and we have chosen to go out and take pictures, we have a strong penalization factor, -1. Our day is ruined. If it is rainy and we have decided to stay home and cook, we are happy, 75%, but not as happy as if we were able to go out and do something nice, like, for example, taking pictures. In fact, if the weather is sunny and we have decided to take pictures, we have maximum satisfaction. If it is sunny and we have decided to stay at home and cook, we are happy, but not that much because we would have preferred to go out and take pictures. Utility functions can vary. You can decide in many ways how to perform utility estimates. Let's keep it simple in here just to show you how to use influence diagrams in Unreal with Fantasia. Before moving into Unreal, it is useful in most of the cases to use PyAgrum, so the Python wrapper around the Agrum library, to play around with your models and check what happens even by using graphical feedback if you're working with Python Notebook. In the future, I hope that we will be able to integrate a graphical editor to assemble probabilistic graphical models in Unreal, but this will not happen soon. So the best way to play around with this kind of models is still to work with PyAgrum. So first of all, we create the influence diagram. Then we add two chance nodes, the weather and the forecast. And we add the labels rainy and sunny, both on the weather and on the forecast node. Next, we add a decision node, which we'll call A for activity. And on activities, we will have both pictures and cook. And at last, we add the utility node, one-dimensional node called U for utility. Next, we create the arcs between the variables, just as we saw in the previous slide. And then we fill the tables with values, probability values. In this case, I am using this kind of strategy using vectors, but PyAgrum has more readable ways to populate the tables. I'm using this version because it's the same strategy that we will use in Unreal. So as you can see, we have the distribution, the probability distribution of the weather to be 0.4, 0.6 for rainy and sunny, just as we saw in the previous slide. Then we have the probability distribution of the weather forecast algorithm. 0.75, 0.25, etc. And we have the utility table. If we inspect the graphical configuration of the graphical representation of the model as we have shown, this is what we get with Pyagrum in a notebook. So we have our prior distribution of what usually is better to do given the information. So since most of the times in this place is sunny and it's easier to predict the sunny weather, so most of the times the forecast will be sunny. In general, it should be better to go out and take pictures. Now let's add evidence to this model. So this is what happens from the data that we collect as priors in our network. Let's assume that we get some feedback from the weather forecast in the specific moment where we have to take the decision, and let's see how the model reacts. So in here, we are setting an evidence for the forecast, stating that there is a 70% probability for the weather to be rainy and 30% for the weather to be sunny. By considering at the same time the priors on both the weather and the forecast, so the kind of error that the forecasting system can commit, and what is generally true inside in the place where we're going to go, the system estimates that it is better to stay home and cook. So the risk is too great to be penalized to go out and take pictures. Now let's switch these probabilities and let's assume that the feedback was that for 30% of the of probability the weather will be rainy and 70% probability the weather will be sunny. Of course, in this situation, the most useful thing to do is to go out, plan to go out and take pictures. But note that the two models are not symmetrical. So although the probability distribution changed in a symmetrical way, the utility this did not change symmetrically because the system is informed that it is easier to predict sunny weather rather than it is to predict rainy weather. And it is also true that in the place where we're going, it is actually sunny most of the times. So it is much more sure about recommending going to take pictures than it is about staying at home and cook, although the probability distributions are symmetrical. So the important aspect of influence diagrams is that they are able to take into consideration probability estimates about multiple variables, utility functions, and the priors that you include in your model. And as you can see, influence diagrams are also quite fast in taking all these aspects into consideration. You get an answer in less than a millisecond. So now let's jump into Unreal and let's reconstruct the same example in Unreal and check that we obtain the same numbers in Unreal. So here's the blueprint that we're going to use for our example. First of all, when the game starts, we create an object of type influence diagram and we save it into a variable. And then we do exactly what we did in the example with Pyagrum. First of all, we add the nodes, the variables. Both of these are chance variables. We have the weather and we have the forecast. Both of them have the same set of labels, rainy and sunny. Next, we add the activity node. So it's a decision node, and its labels are pictures and cooking. Then we have the utility node, variable u, description utility, the type of node is utility, and we just have a one-dimensional utility. Next, we create the structure, so we add the arcs from W to F, from F to A, from A to U, and from W to U. And then we fill the tables. So for the chance nodes, we use the fill CPT function, and we use 0.4, 0.6 for the probability of the weather being rainy or sunny. Then we have the same distribution in here, so these values to predict what's happening when the weather is actually rainy and what happens when the weather is actually sunny. The precision of the estimator is here. And we have the utility table in here. So we have set up and configured the general structure of our influence diagram. With this event that fires when I press spacebar, the influence diagram runs the make inference function, so it actually is able to compute the posterior probabilities for the action variables. We take the outcome of this getPosterior function, and since it is referring to the action variable, we know the distribution over the pictures and cooking labels. And we print them. So green is pictures and red is cooking. Next, we have a 5 seconds delay. After 5 seconds, we add evidence to the influence diagram, and we set an evidence over the forecast variable, stating that we have 70% probability that the weather will be rainy and 30% that the weather will be sunny. So it's the first of the two examples that we saw before. Again, we make inference over the network, and again, we get the posteriors over pictures and cooking. So first, we should get the posterior probability of going and taking pictures or cooking when we don't know anything. And after this, we have the same distribution after observing the weather forecast. So let's run the example and let's see what happens. So first of all, we get 61, 39, 61 for the pictures, 39 for cooking. But then, after seeing that the forecast is bad for pictures, we get 40 for the pictures and 60, or less 60, for the cooking. These are the same numbers that we saw in the Pyagrum example. So we have reconstructed the example inside Unreal, and we have run an influence diagram inside Unreal. Influence diagrams can become very complex. You can also combine multiple utility nodes, multiple decision nodes, etc. This will be a topic for a more advanced tutorial about influence diagrams and their relationships with conversational AI. If you want to have a general idea of the role of influence diagrams to build interpretable conversational AI, as we are doing at the University of Naples, Federico II, I recommend you watch the dedicated video about how to create hybrid conversational AI with Fantasia, so that you can get the big pictures from there. So this is all concerning this first introduction to influence diagrams. Thank you for listening and have fun with Fantasia.